All right, so page 13 of your packet. So today we're going to talk about, the first thing we're going to talk about is the method of common bases. So how to solve exponential equations with that common base. Now, the reason your power chart, I wanted you to have it out, is because that power chart is a really good tool to use when you're trying to figure out what the common base is. So remember, when we're talking about an exponent, let's say you had 2 cubed. Which number is the base? Which number is the exponent? 2 is the base, and 3 is obviously the exponent. All right. The reason we want to know that is because when we do common bases, we're essentially going to be changing the one side of the equation to have the same base as the other. And the reason we do that is because the great thing about common bases is that once you have the same base, you can eliminate the bases, break down within the exponent, and then solve it like a linear equation. All right. So most solving exponential equations involves technology. This is one of the few that do not involve technology. So this is one of the ones where you don't necessarily need a calculator to solve for, but it only works in very special circumstances. All right. And it's called, again, the method of common bases. Or you may hear it as same base method, like base method, whatever. Whatever synonym for common that you hear. Now, we're going to solve each of the following examples using simple exponential equations by writing the equation that has a common base. So, let's look at the first example. So, what I want to do is change one or both sides of the equation so they both have the same base. So, look at the numbers themselves. All right. Then look at your power chart. What base do 2 and 16 share? So if you're looking at your power chart, the bases are the side across the top, I believe. Yeah, it's across the top. Yeah, it's across the top. So look at the row across the top and figure out what base 2 and 16 share. And that would be the common base. So in other words, if I'm looking at my power chart, all right, if you're looking at your power chart, you want to find where the number 2 and the number 16 are in the same column. All right, and the number that's at the top of that column, that's the common base. So by column, I mean like up, down. So where are 2 and 16 in the same column? For what base? Which is the highlighted green at the top. For 2. So we're saying that 2 and 16 have a common base of 2. So if we have a common base of 2, we're going to change this so that both are going to have a base of 2. So we have 2 is equal to 2. Now, since the first side or the left side is already has a base of 2, we're just going to leave it as is. So 2 raised to the x power. But now we got to change 16 to be in the form of 2 raised to some power. 2 raised to what power equals 16? What does your power chart say? Right, 4. So we're going to say 2 to the 4th power. So all we did is write an equivalent expression. All right, this is the exact same equation as the one above it. We just rewrote it so that they have the exact same base, which that base is 2. All right. Now, here's the great thing about like bases. As soon as you have a like base on both sides, you can eliminate them and bring down their exponents. So x equals 4. So that's the great thing about like bases. As soon as you have a like base, you can eliminate the bases, bring down the exponent, solve the equation. So it turns into either like a nice linear equation or maybe a quadratic equation occasionally, but it turns out being an equation that you already know how to solve. The hardest part is finding that like base. And we can check our answer. If we plug 4 back in for x in the original equation, 2 to the 4th is equal to 16, right? So if I plug the 4 back in for x right here, is that a true statement? 2 to the 4th is equal to 16? Yes, so that's clearly the answer. All right. What about letter B? 3 and 27. What's their common base? So look at your power chart. 3. 3 is definitely their common base. So since the left side already has a base of 3, I'm just going to bring it down. Now, 3 raised to what power is 27? The third. Good. So we now have common bases. The bases go bye-bye. And the exponents come down. So x is equal to 3. Now, these are like the super, super basic ones. We will get a little bit more difficult in difficulty in a minute. All right. But it's a good way to see the process of at least switching the bases. All right. The last one. Or no, letter C. So letter C is a little tricky, but they do have a common base here. Look at 5 and then 1 over 25. What's their common base? 5. So they both can have a base of 5. So 5 to the x is already a base of 5, so we just bring it down as it is. 5 raised to what power is 1 over 25? It is possible. -2. Because remember, negative powers, you would do 1 over, the negative will go in the denominator, so it would be 1 over 5 squared, so 1 over 25. Got the same base, eliminate, bring down the exponents. X is equal to -2. Now, D is a little bit different, but it is possible. So this one's a bit of a thinker. What's this common base here? 4. I would definitely say 4. Now, or the common base could also be 16. All right, so I'll show you with 4 first. So 4 is already turned into the common base, but what's the exponent of 4 if there's nothing there? 1. So we're going to raise that to the first power. Now, I'm going to put parentheses around this 4 and put the x on the outside because we still got to multiply whatever it is to the x power. 4 raised to what power is 16? 2. Now, we would then, because that x still exists with the 16x, we could do the power rule, meaning multiplying the two exponents together. So we actually have 4 raised to the 2x is equal to 4 to the first. Because we still have to account for the exponent that's already there. All right. 4's go away. We bring it down. So 2x is equal to 1. Now, it's not fully solved. What's the last thing I got to do? Divide both sides by 2. to get the x by itself. So x is equal to 1/2. Now, the other way we could have done it is if I had a base of 16 for both. It does work this way. So 16 to the x power. Now, I'm going to tell you right now, because we already solved using base of 4, that this would be 16 raised to the 1/2. Why does 16 raised to the 1/2 give me 4? What's the equivalent of that? So look at your power chart. It's actually written on there. 16 raised to the 1/2 is the same as what? The square root of 16. So this works because 16 raised to the 1/2 is the exact same as the square root of 16. Remember, fractional exponents mainly talk about roots. All right. So 16 to the x power, you could have done it that way. Now, if you did base of 4, a little bit more work, but you still get the same answer. Because sometimes you do have more than one common base, but it's really just a matter of pick which one you like to work with more. All right. Now, before we go into some harder ones, we're now going to look at something that we need to review pretty much. So we kind of touched on this with letter C, or letter D, I'm sorry. So sometimes that common base, we have to already has an exponent. And we have to exploit the fact that manipulating both sides, that they have to have a common base. But we also need to review an exponent law, which I already mentioned. So this law that we have to review is called the power rule. And it essentially states that if you have a base raised to an exponent and then it's all raised to another exponent, all you got to do is distribute the exponent on the outside to the exponent on the inside. So you're multiplying them together, just like you would distribute in an equation. So this is the exact same as x raised to the 3 times 2, or x to the 6. And the reason we have to do this is because occasionally, just like we had with letter D, depending on how we change the base, and guys, you can turn off the light if you need to. I know it's kind of light. Depending on the base, all right, you may have to already eliminate, or you may already have an exponent connected to that base, but you still have to change the base, all right? So to make sure the equations are good, we still have to do the power rule to those bases, all right? So just to review power rule, let's simplify these expressions. So for letter A, all we do is multiply the 3 to the x. So this would be 2 raised to the what? 3x. We just multiply 3 times x. For B, multiply the 4x to 2. So this would be 3 raised to the what? 8x. Because 2 times 4x is 8x. All right, be careful about this one. Multiplying 3x minus 7 to negative 1. So think about it as negative 1 times 3x minus 7, like it's distributing. All right. So we would have 5 raised to the what? Right. If we distributed, negative 1 times 3x is negative 3x. Negative 1 times negative 7 is positive 7. So if you have like an expression in the exponent, just treat it like it's a distribution problem. Like write it off to the side if you need to see it better. However you want to do it. Same thing with this one. We have 1 minus x squared times negative 3. So we can rewrite this as negative 3 times 1 minus x squared and then distribute. So we have 4 raised to the what? So we would have negative 3 plus 3x squared. Now, if we wrote it in standard form, it would be 3x squared minus 3. But I'm just keeping order for right now. Everyone understand the basics of the power rule. So this is about the hardest you would have to do with the power rule. Very, very basic use of the power rule in this case. All right. In terms of solving these equations, that's a very basic power rule. Any questions on that? All right. Now we're going to work on finding a common base for each side. So previously, they already kind of told us what the common base was because one side already had the common base. Now we're going to look at where we have to find the common base for both sides. So again, that's where your power chart comes in handy. You want to look for where those two numbers are in the same column. All right. So 8x equals 32. What's the common base there? Look at your power chart if you need to.
2.
It's 2. So we would have 2 raised to the something x on the outside because that x still is there. And then 2 raised to something. 2 raised to what power gives you 8? 3. 2 raised to what power gives you 32?
Sorry, I can't help you with that.
Siri, hush up. Go away.
Okay.
Oh. The back of my phone is that sensitive and it's all the way over there. So yeah, 2 to the 5th is 32. Now, we do need to do a power rule on the left side. So we have to do 3 times x, which is what? 3x. So we have 2 raised to the 3x is equal to 2 to the 5th. Now what do I do? Right. We can cross the bases out, bring the exponents down. So this is now 3x is equal to 5, which what's the only thing I got to do to solve? Divide by 3. X equals 5/3. See, with these, this is when they start getting weird and you can't just kind of guess and check it. Because it could be something weird like that fraction. Yes. Yeah. All right. What about for letter B? So we have a base of 9 and a base of 27. What common base do they have in common? Right. It is 3. So don't be confused with multiplication. 9 is a factor of 27, but 9 squared is not 27. All right. So we're going to turn this into bases of 3. Now, I'm going to put on the outside of my parentheses, since we have something that already has an exponent, 2x plus 1, so I know it's still there. And I know I'm going to have to do a power rule. 3 raised to what power is 9? 2. 3 raised to what power is 27? 3. What's my next step here? Not yet. I gotta do something else first. Right, we gotta do the power rule first. So if I wrote off to the side, I have 2 times 2x plus 1. If I just distribute it, I get 3 raised to the 4x plus 2 is equal to 3 to the 3rd. Now I can cross out the bases. I just want to have one singular exponent when I cross out bases. So the 3's go away. I get 4x plus 2 equals 3. Now we have a very, very nice linear equation that you've been learning how to solve since Math 1. All right. What's my first step to solving this equation? Subtract the 2 from both sides. 4x is equal to 1. Then what do I do? Divide by 4. So x would equal 1/4. All right, last one, at least for this section. All right, so we have x's on both sides, but we still need to make bases first. So, again, you might want to look at your power chart for this. What's the common base between 125 and 1 over 25? Definitely 5. So we have 5 raised to something power all raised to the x. And then 5 raised to something power all raised to the 4 minus x. 5 raised to what power is 125? 5 cubed. 5 raised to what power is 1 over 25? -2. And again, that's why I wanted you guys to have your power chart out, because if you can look at your power chart, it's quick. All right. Some of them you may not have to know off the top of your head, but I will let you use this power chart on your tests. So you don't have to keep kind of putting in your calculator and being like, okay, cube root of this number. It's a lot easier that way. So now I got to do the power rule twice, one on both sides. So 5 cubed raised to the x power. 3 times x is just 3x. So 5 to the 3x is equal to, if I do -2 times 4 minus x, I'll write it off to the side just so I know I'm distributing. -2 times 4 is 8, or -8, my bad. -2 times -x is positive 2x. What comes next? Yep, the 5s go bye-bye. So we have 3x minus 8 plus 2x. Now, we have variables on both sides, but you should know what to do with this here. What do we need to do first if we have variables on both sides of a linear equation? Right, we got to move one of the x's to the other side. I suggest the smaller one because then you're still dealing with positive numbers. So I'm going to subtract the 2x to the other side. This cancels. 3x minus 2x is just x, or 1x, and it's equal to -8. And we're done there. Any questions on having to do the power rule, changing the bases on both sides? It's not too bad, right? Like, this is the easier version of solving exponential equations. And again, you can only do this in special cases because more often than not, an exponential equation will not give you like bases. But we'll learn later this week what you do with that. But when you do have like bases and you recognize it, it's really nice and easy to do. Or simpler, I should say. All right, last one. Example 4. So we're given this equation. So 2x squared minus 3 is equal to 64. Now, instead of a linear equation, we're going to end up with a nice quadratic equation. All right. So first off, let's just get the bases down so we can eliminate bases. So between 2 and 64, what's the common base? Someone who hasn't talked today, what's the common base between 2 and 64? Look at your power chart if you need it. Right, it's 2. So base of 2 is already base of 2, so I leave it as 2x squared minus 3. 2 raised to what power gives you 64? 6. So we have like bases. These are gone. I get x squared minus 3 is equal to 6. Okay, now, here comes the pain in the butt part. So recall back to math 2 when you were solving quadratic equations a lot. If you ever solve a quadratic equation, what's the first thing that you got to have? So one side has to be equal to what? 0. With a quadratic equation, one side has to be equal to 0. So we need to move something over to the other side. What should I move? The 6. I'm going to subtract the 6 to both sides. I get x squared minus 9 is equal to 0. Now, there are a couple ways that you can do this. You can either factor if it's factorable. You can also do the quadratic formula if it's not factorable. Or you can use the quadratic formula regardless. Just a reminder, the quadratic formula is this. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. When you have ax squared plus bx plus c equal to 0. All right, so your a, b, and c values are just the numbers in front of the variables. I would write that down because you will see it again. Now, the good thing about this quadratic is that it is factorable. X squared minus 9 is an example of what type of polynomial? Does anyone remember the name of it? I'll give you a hint. DOS. What does that stand for? Think back to when you were factoring. You did a lot of it last semester or last year, Math 2, as well as in Math 1. I'm literally teaching this to my Math 1 kids right now. Do you guys remember difference of squares? So this is a difference of squares problem, meaning that when you have two perfect squares being subtracted from each other, it's a very easy factor. So just to recant, this is a difference of squares. And how it looks is that if you're given a squared minus b squared, all right, the way you factor it is you essentially take the square root of both terms and you have a plus b times a minus b. That's how you factor it. So my x is x squared is a squared. This is my a squared, this is my b squared. So what's the square root of x squared? X. So that means I'm going to have x plus something, x minus something. What's the square root of 9? 3. So I have x plus 3, x minus 3, all equal to 0. Who remembers the next step from there for solving that quadratic function? What do I do with those two factors to solve? Right, we set them both equal to 0, solve them individually. So x plus 3 is equal to 0, x minus 3 is equal to 0. So subtract 3 to both sides. X is equal to negative 3. Add 3 to both sides. X is equal to positive 3. So we could state that x is equal to plus or minus 3. All right. So guys, you will be thrown a quadratic one every once in a while. So be careful about that. So you got to remember your factoring skills, because if you don't remember factoring, you will remember by the next unit, because the next unit's all about it. All right. Yes. You'll trust me, you'll be using factoring for like the next 2 units. So unit 3 and unit 4 are very factoring heavy. So we're going to make sure if y'all don't remember how to factor, I'm going to make sure you remember it. All right. Any questions on that? All right. So now we're going to break away a little bit from exponentials and look at logarithms because they do connect. So let's look at 2.3, so page 15 of your packet. So this is the second part of the notes for today. So, I think it's only one. Maybe two, but they're short. We're just talking about logarithmic form specifically. We're not actually solving anything. All right. So the great thing about exponentials and logarithms are inverses of each other. All right. We covered inverses in the last unit. Who remembers what that means? So what does it mean for it to be an inverse function of a function? Yes. The x's and y's essentially switch places if you're looking at it from a table perspective. They also undo each other. All right. So one undoes the other. So exponential functions and their inverse functions or reverse are called logarithms. So the inverse of an exponential will more likely than not be a logarithm. That's why in the last unit, we didn't even touch exponential functions when we were doing inverses because you haven't learned what that inverse type is. Now, look at exercise 1. So, they gave you a table already filled in for when f of x is equal to 2x. All right. Now, they also already did some paper and graphed it for us. First off, they want us to know if it's a one-to-one function. Who remembers what it means to be a one-to-one? Jasmine. Right, the graph passes the vertical line test and the horizontal line test. Look at the graph, which is the curve right here. Don't worry about the line. But look at the graph. Does it pass the vertical and horizontal line test? Yes, so it is one-to-one. Now remember, if it is a one-to-one function, this is review from unit 1. If a function's a one-to-one, it has an inverse that is also a function. All right. So that's part B. The inverse must also be a function, meaning that it will pass the vertical line test, or none of the x's will repeat. So if I want to write or make a table for the inverse of f of x equals 2x, what's the only thing I got to do between the two tables for the inverse? Switch the x and y columns. All right. So all we're doing for this, for the inverse, is we're going to switch x and y points. So this is now 1/8, 1/4, 1/2, 1, 2, 4, 8. This is now -2, -1, or nope, my bad. -3, -2, -1, 0, 1, 2, 3. Didn't even have to do any calculations. They already gave us the table. They were nice. They gave us that original table. All we had to do was switch the x and y columns to get the new table. All right. So if we graph this function really quickly, I would have 1/8, -3, so about right here. 1/4, -2, so right here. -1, 1/2, -1. 1, 0. 2, 1. 4, 2, and 8, 3. So the graph will look something like this if I just plotted it very quickly. which remember, that actually is the correct inverse graph because we talked about this briefly last unit, but remember, f of x and f1 of x are symmetric across the line y equals x, or they just reflect across the x-axis, or they reflect across the line y equals x, which is why that line is on that graph. If you flip them over on each other, they're perfect reflections. But that's kind of, you don't really need to know that for this. That's just review. Now, if we were to solve this algebraically, so recall back to unit 1, what was always the first step if I wanted to find the inverse of y equals to the x power? What's always the first step to finding any inverse if we're solving for the inverse function? We switch the x and y. That's our first step. So our first step is to switch x and y. So if we did that first step, we would get x is equal to 2y. And we're going to stop there for right now because this is where logarithms come in. All right. So the logarithm part comes in when we're actually solving for this logarithm. So the function of y equals log b of x, that's a logarithmic function. It's that weird function in your calculator. You know how your calculator, you always saw the word log on there? That's what it's for. It's for a logarithmic function. Is the name of the inverse of y equals bx. So, for example, y equals log 2 of x is the inverse of y equals 2x. Now, here's how you do it. All right. We do something called loggy froggy. It sounds dumb, but you'll see why I call it loggy froggy in a second. So when you're solving for any logarithmic or exponential equation, all right, if I look at this, y equals log b of x is the same as, it's the exact same as, stop moving, the same as the base y equals x. Now, the b, the little tiny b next to the log, still represents the base. So it's the same thing as like an exponential base. All right. The y in a logarithmic is typically your exponent. And your x is called, oh, it's a big word. What is it? Your argument. So if we look at it from the exponential perspective, b is still your base, y is your exponent, and the x is your argument. All right. And all the argument's saying is that we're saying it's equal to whatever. So logs and exponents, just take that information, put it in different places. Now, here's how loggy froggy works. So let's just start with the inverse, by equals x. All right. This is how loggy froggy works. So basically, we're putting it in the order of, our angle is log b of x, I like the parentheses around that, is equal to y. And we're trying to get it in the order of base, argument, exponent. That's the order. So we always start at the base with loggy froggy. And we're going to hit the x, hit the equal sign, hit the exponent. Now, the reason this is called Loggy Froggy is because this whole movement kind of looks like a little frog. Ribbit, ribbit. All right. And what that means is that when we put it back into this log form, we would write log b of x, because that's our next step. So we start here. So boom, that's the first point. Boom, that's the second point. So log b of x, that's the second hit, is equal to, that's the third hit, y, which is your last hit. So essentially, it's telling you the order of which you're going to write things in. It also works with logarithms. So for example, if I did log 2 of x is equal to y, all right? If I swung things around, I would start here at the base because that's my little number for a log. I would boom, hit at the y, boom, hit at the equal sign, and boom, hit the x next. So then when I put it in the form b to the y or b to the x equals y, I first have the base, which is 2. That's my first hit. Raised to the y power, that's my second hit, is equal to x. That's my third hit. So with exponentials, you're going 1, 2, 3. And we'll have some more practice with this, so don't worry about it. But again, this method is called Loggy Froggy. So if you hear me say it a lot, that's why. It's the easiest way to convert between exponentials and logs. Now, let's look at some examples. So we're going to actually evaluate some logs. Now, the easiest way to evaluate a log, in my opinion, is to set it equal to x and convert it to an exponential using Loggy Froggy. So if I'm using Loggy Froggy, I always start at the what for either a log or an exponential. It doesn't matter. You always start where? At the base. Where's my base for this log? It's the 2. So we always start at my base, which in this case is the 2. And we're always going to go counterclockwise. So we will get 2x equals 8. So if we put it into the form bx equals y, we get 2 as our base. That's our first hit. Raised to the x power, that was our second hit, is equal to, that's our third hit, 8, which was our last hit. So we can either do same base, or can you guys figure that out right off the top of your head what x is equal? 2 raised to what power is 8? 3. So in this case, this logarithm is equal to 3. So you could have done same base, but in this case, since we're just evaluating the logs, it's pretty straightforward what it is. So it's almost like you're going backwards, all right? So it's almost like you're trying to find what the exponent is. That's what your logarithm is equal to. So in other words, we're saying that it's equal to this number. So we know we have a base of, like for letter B, the base is 4. We know that 4 raised to something is equal to 16. That's how you would read that log. Or if you wrote it in Loggy Froggy form, set it equal to x. Go boom, 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 starting with the base. So we would have 4 to the x is equal to 16. 4 raised to what power 16? To the second power. And that's essentially what you would do for all of these. So look at letter E. All right. Where do I start if I'm going to do loggy froggy first? So first I'll set it equal to x. Where do I start for loggy froggy? What's my base? 6 is your base. So we start at the 6. We're going counterclockwise. We hit boom at the x, boom at the equals, boom at the 1 over 36. And then we write that in the appropriate order. So what would my equation be? In exponential form. So we know we start with a base of 6. And it's raised to what power? The x power, because that's our next stop in the loggy froggy train. It's equal to, what's our last stop? 1 over 36. Now, again, you can do this as same base method, or you can just look at your power chart and figure it out. 6 raised to what power gives you 1 over 36 if you're just looking at your power chart? -2. So if we evaluated log 6 of 1 over 36, it would be -2. All right, last one. Let's do H. So set it equal to x so I can do loggy froggy. Where's my first stop for this train? So we start at 3, which is our base. Where's our next stop? X. Where's our next stop? Equals. Last stop. The 5th root of 9. I'm assuming you just didn't know how to say it. 5th root of 9. All right. So if I write in order, I start with a base of 3. It's raised to what power? What's the next stop of the train? X. And it'd be equal to what? Square root, or not the square root, 5th root of 9. Okay, now this one you might have to do same base. First things first, I would convert that root to a fraction. All right. So I'm going to bring down the 3 to the x. How would I write the 5th root of 9 as an exponent? So 9 raised to what power is equivalent to the 5th root of 9? So think about it. The square root of 9 is equivalent to 9 raised to what power? Look at your power chart. What does it say at the bottom when it came to roots? Mm-hmm. So is it not true that the square root of 9 is equal to 9 raised to the 1/2? Is that true? Put in your calculator, see if it's true. We know the square root of 9 is 3, so what's 9 raised to 1/2? You put in your calculator. It's still 3. So essentially, if we raise it to whatever the type of root it is, like 1 over whatever the root number is, it's the same thing as taking that number root. So the 5th root of 9 is the same thing as 9 raised to what? Not 1/2, but 1/5. Because we're taking a 5th root. So I'm doing that because remember, there's an unspoken 2 outside of a square root. So I'm taking this number on the outside. I'm taking this number on the outside of the root, putting it under 1, and that's my new exponent. Yes. Yeah. Now, changing the base of the 9. We know it has a base of 3. So it's be 3x is equal to 3 squared, all raised to the 1/5. Power rule. This would be 3 of the x is equal to 3 raised to the, you multiply the fraction, so straight across, 2 times 1 is 2. 1 times 5 is 5. Bases go away. What's x equal to? 2/5. So sometimes you can look at your power chart, but sometimes if you get a weird one like that, loggy froggy, and using same base is probably the best way to go. But you do need to know how to convert a root into a fractional exponent. And that's review from Math 2, guys. So if you have issues with that, you need to see me about that. All right. So there's two more things that I want to cover real quickly. It's very, very quick. All right. So putting logs in your calculator. That's the thing I want to cover. All right. For exercise 4, it asks us what log 3 of 40 is. That is a number. All right. So watch this. In your calculator, this log button right here does not give you a log with a selectable base. It gives us what we call the common log, which we'll talk about in a second. So do not use that log button if you have a little number in the base. The way you get a log with a changeable base, hit the math key and scroll down. You're going to have to scroll down a little bit. All right. Where it says letter A, do you see how it says log base? So right here, if you scroll down using your arrow keys after you hit the math key, do you see where it says log base? That is where you can input a logarithm with a specific base. So you would hit enter. Now we can put in the base that we want. So we'll put 3 and then 40 and hit enter. And so the number that we get is like 3.36 if we round it. All right. So remember how to do that, because occasionally you may have to evaluate some logs that are not nice. All right. That's a good way to check it. So it would be between 3 and 4. Now, here's the other part. The common log. So most calculators only have 2 logarithms that they can evaluate directly. One of them is log with a base of 10, and this is known as the common log. The other one is called the natural log, which I'll talk about in just a second. So common log looks like this. Because it's known as the common log, whenever you see log without any base, that base is not 1. The base is 10. So the common log always has a base of 10. All right. So for example, if we put just log of 100 in our calculator, this is one where you can hit the log key to the left of the 7, because that inserts automatically the common log. That's why you never use that key if you have a different base besides 10. All right? Never use that key if you have a base, like a little number in the base besides 10. Never. All right? So we have log of, let's say, 100. Hit enter. It's 2. Which makes sense because 10 squared is 100. So that's the common log. The other one, I would just make a note of this. We won't use this too much in this class, but it's good. I like this a little bit more than common log. It's what we call the natural log. So there's 2 different types of like standard logs. The common log, which has a base of 10, and the natural log. The natural log has a base of E. Remember E? We talked about it yesterday. It's a number. It's similar to pi. Now, the way you would see log base E. So if we wrote log base E of x, that's exactly the same as ln of x. So that's the other way you see logs. All right. Now, natural log won't really come in handy until we do exponential equations with unlike bases, but it's a good thing to mention just so you know that it does have a base of e, which is that number e. And so that's the key that is on your calculator. That's the key directly below the log key. That's your natural log key. So that'll be your natural log, ln. All right. Any questions? Okay. So classwork wise for today, work through that evaluating logs worksheet just to make sure you guys have a solid understanding of logs. So a lot of it's just asking you to do exponential form, so loggy froggy to convert it, as well as evaluate some of the logs like we just went through. Besides that, there's also a quizzes that's already open to you guys about exponentials and logs. That won't be due till tomorrow at midnight, but we got about little over 15 minutes, so you could probably knock out a little bit of this. That quiz is already available to you, but if you don't get to it, it's fine. But you do need to have it done before test day at the very least. All right. So no new Delta math, but we do have a quizzes instead of a Delta math. All right. So I'm going to post the exit ticket. And it's fairly straightforward. Not too bad. Not too bad. All right. So it's just solving an equation, same base. All right.